All right. Hello, everyone. Welcome to our robotics colloquium. We meet every Friday at 1:30 and have several distinguished speakers. And today we have Tyler from UT Austin. Tyler is doing his postdoc at UT Austin. Before that, he got his PhD at UC Berkeley, working with Shankar Shastri, who, fun fact, is my wife's uncle. Now that explains everything, hopefully. Tyler's done some really, really great work combining traditional control theoretic techniques with modern data-driven techniques that are used in machine learning, deep learning. And today we'll get to hear about some of that.
Yeah, thank
Take it
you
away.
for the introduction. Very happy to be here, and been really great to meet a lot of you and get to meet a few more of you later this afternoon. So while we're trickling in, I think at a really high level, what this talk is about is trying to understand how we can build scalable but methodical engineering pipelines, which are going to enable us to systematically push robots out into real-world applications. And to some extent, we're really in luck. We've been able to engineer these fantastically complex machines, which are really just capable of performing so many amazing things. On the other hand, and I know this video is cliche to show at this point, we're still really struggling to systematically put these systems out in the real world at scale in a way that is economically viable. And there's a lot of challenges from the control side, which are really making this difficult. These systems are very difficult to model. Their interactions with their surrounding are even more difficult to model. We want them to perform these very complex behaviors. They're high dimensional. They're highly unstable. Basically, just in current practice, it's just not really reasonable for us to systematically beat these systems into doing what we want out in the real world in a way that is economical. Now, I originally made this talk for a general audience, but it's worthwhile just sort of reflecting on a second what it means to actually control these systems. So we have some object in the real world, like this quadruped, and we want it to do something like walk forwards and not fall over. And it's going to have a state x and an input u. So the state x are things like the positions and velocities of the joint of our robots, and the inputs are everything that we have control over, so things like the commands that are going to our motors. And we're going to understand the system as evolving dynamically over time. So at some time t, we'll choose some state x, or we'll have some state x, we'll choose some input u, and a little while later, we'll get some new state. And what we're going to think about very carefully today is how we can, in a very systematic way, build up the feedback loops we're using to control these systems. In particular, we're really going to focus on how we can synthesize a policy pi, which will, at every state x, choose the input we want to put into our system to really control how these systems evolve through their surroundings. And as Sid was really sort of hinting, there's really been this sort of titanic clash over the last decade or so, really trying to understand how we can reconcile or bring together techniques from control theory and AI and machine learning. But at the same time, I would argue that over the last decade, we've still seen these approaches as sort of different design paradigms get further and further apart. So control theory is really what you think of when you think systematic, disciplined engineering pipelines. And more, we've seen AI and machine learning being pushed towards trying to soak up as much data as possible to try to control these systems from scratch. And what we're going to try to understand is how we can really bring together these design philosophies at a very sort of deep level throughout this talk. In particular, for the purposes of this talk, we're going to try to understand how we can bring together ideas from feedback control and reinforcement learning. And I'll give you some indications at the end of the talk how the general principles I'm going to identify here extend more broadly. So before we get into it, I think it's worthwhile to sort of get in the mindset of what it actually looks like to engineer these systems with these two approaches. So feedback control is really about models. And if you're a control engineer, you spend all of your time thinking really hard about a physics-based model and trying to understand how to exploit known structures in that model. We do this so that we can systematically build up very well-structured feedback loops which exploit those structures, and we'll get these systems to systematically do what we want in the world. Now, these approaches are very powerful because they leverage known structures in a way that enable us to design feedback controllers which make our control strategies robust to differences between our models and reality. On the other hand, at some point, our models fail. We can't cram every feature of the real world into a rigid body model, and at some point, our models are going to fail, and our control architectures that we build upon them are also going to fail. And moreover, we just can't write down everything we want these systems to do out in every situation they're going to encounter in the real world. And so these challenges are really what have led to a lot of excitement around reinforcement learning the last decade or so. And the way I like to think about this is that what reinforcement learning really does is it shifts the role of the engineer. So instead of sitting down and spending a lot of time with pen and paper thinking about the physics of your system, now you define a reward function for your robot. So this provides points for the robot walking forwards and not falling over. You feed this to your algorithm and you suck up a bunch of data, and then your algorithm is going to chug through a bunch of computation and hopefully spit out a controller. Oftentimes today, it'll be a neural net. And the hope here is that this algorithm will get the system to do what you want. And these approaches have really shown a really fantastic ability to, in a sort of emergent fashion, synthesize controllers with very complex behaviors. Moreover, at least in principle, you don't need to know the dynamics for your system. We have the opportunity to go and learn to control these systems from scratch using real-world data. On the other hand, because these approaches don't leverage known structures in the dynamics, they're oftentimes too either inefficient or too unreliable to actually go train with real-world data. And so what do? A lot of times today, we actually train these approaches in simulation. Now, this is really powerful because it enables us to explore the full range of behaviors these systems can display, but at the same time, we run into the same problem as we do with classical control methods. We have this simulator, we want to deploy these systems in reality, and there's fundamentally just going to be this gap that we need to somehow overcome. And so if we put these two approaches up next to each other, it's really tempting to try to understand how we can get the best of both worlds. And the approach we're going to take today is to systematically embed design techniques from feedback control into the reinforcement learning problems we're setting up. And this is going to give us a number of nice features. So it's going to enable reinforcement learning algorithms to explicitly leverage known structures in our approximate physics-based models, but it's also going to leave us with the flexibility of reinforcement learning methods to overcome nonlinearities, which are too difficult to model in the real world using real-world data. And what we're going to do is we're going to use feedback control as really the glue that's going to hold everything together and let us get the best of both worlds. In particular, we're going to build up analysis and design techniques which bring in ideas from optimal control, machine learning, and optimization theory, and which are going to enable us to write down reinforcement learning problems, which enable us to go from initial solutions designed in simulation to controllers which perform well in the real world using small amounts of real-world data. So just to give you a bit of a preview, so part one of the talk is going to be about using known control architectures which are built around our physics-based models to perform principled reward shaping for reinforcement learning problems. And in part two, we're more explicitly going to try to understand how we can co-design the reinforcement learning algorithms we're writing down and the control architectures we're optimizing over to really squeeze the most out of our approximate physics-based models. So since this is my first time at UW, I just want to give you a little bit of a better sense for my different work. So the two pieces of work I'll be talking about today fall sort of very squarely in the middle of AI and machine learning and control in the context of robotics. But I've really had the opportunity through a number of collaborations to work all across these spaces. But really the sort of key thing that brings together all of this work is really using our approximate physics-based models to really understand the structure of the optimization-based control problems we're writing down to design them more effectively. Okay, so before we get into the sort of technical meat of the talk, I want to go through a little bit of a primer on reinforcement learning just to set up the problem we're going to look at, and also to really dig into some of the core technical challenges that we're going to try to overcome in the context of robot learning. So in our setup today, we're going to, again going to try to control some real-world physical system with some dynamics that are unknown. We're going to treat those dynamics with this map F here, which takes in a state, an input, and gives you your next state. We're going to assume we don't know these dynamics, and then we have some approximate physics-based model for the system, and we're going to try to control the system using reinforcement learning by finding some policy pi, which gets the system to do what we want. So the way we're going to do this is we're actually going to use costs. But what we're going to do is we're going to write down a cost L that is applied to every state X. We're going to penalize long horizon costs, and we're actually going to penalize over a distribution of initial conditions so that we can get a controller which performs well everywhere in the state space. We're going to look explicitly at policy optimization algorithms in this talk. So we're going to try to find some policy which you can think of as some function represented by your neural network. That's a little pi, and we're searching over the space of functions your neural net can represent with big pi here. And at a very high level, the way policy optimization algorithms work is you start with some initial controller, and in an iterative fashion, you go collect real-world data using your current policy. You write down the sort of rewards that you get from this, and then you use that to update your controller and hopefully improve the overall performance. Okay, so really the core challenge in a lot of robotics tasks, and the one we're really going to focus on here today, is that a lot of robotics problems are fundamentally long horizon, in the sense that we have to coordinate the inputs we're putting into the system over long periods of time to get the system to do what we want. So if we think of this carpal here, in order to successfully perform the swing up motion here, I need to coordinate the inputs I'm putting into the system over a long period of time to perform this very non-myopic move back and forth motion so that eventually I'll get the system to perform this swing up. And this is a challenge in reinforcement learning methods, whether you're working in the tabular case or in robotics. But the reason why this is very difficult in robotics is because our systems are very unstable. And I'll talk a little bit more about what this means technically in just a second, but intuitively, it just means that if we don't control these systems very carefully and precisely, they're just immediately going to fall over. What it means is that these systems are highly sensitive to changes in our control policy, which leads to all sorts of algorithmic challenges. And this is really the source of a lot of the inefficiencies and issues with the reliability with these methods. Unstable dynamics lead to algorithm instabilities. And again, the punchline here is this means we have to collect too much data to use these approaches in practice if we're going to go and try and learn in the real world. And again, what we're going to try to do in this talk is try to understand how we can use feedback control to overcome these challenges. And in part one, we're going to do this by using design techniques from feedback control to explicitly bake in known information about our long horizon objectives into the problems that we're formulating. And in part two, we're going to explicitly do this by trying to co-design the policy architectures we're optimizing over and model-based policy gradient methods to really squeeze the most out of our approximate models. And again, really, this is the sort of the high-level picture I want you to have, where what we're trying to do is we're really trying to understand how we can squeeze as much information from our models and from feedback control into the problems that we're formulating, and these are really the two avenues along which we're going to do this. Okay, so again, in part one of the talk, we're really going to try to understand how we can bake in long horizon behaviors into the objectives that we're solving to make the reinforcement learning problems we're formulating easier to solve to get the system to do what we want. And I'm going to give you a really sort of general way of doing this, but for the purposes of exposition, we're first going to focus on learning stabilizing controllers. So we say that a policy pi is going to asymptotically stabilize the system if it drives every trajectory of the system to some goal state. So we're going to take that to be the origin for the purposes of this talk, and pictorially, it just looks like this, right? Every trajectory generated by the policy of your system is going to drive the system to this point. And again, just somewhat formally, this just means that every trajectory of your system will eventually converge to the origin. Now, in reinforcement learning, the typical way we try to combat these long horizon behaviors is by introducing a parameter called the discount factor. So I'm going to denote with gamma, and it's going to lie between 0 and 1. And to understand the effects of the discount factor, let's try unrolling the cost to see what's going on. So by repeatedly multiplying the running cost by gamma as time goes on, what I'm really doing is I'm saying that as I make my discount factor smaller, I care more and more about what's happening over the next few time steps and less about what's happening in the future. So in the extreme case, when gamma equals 0, I only care about what happens over one step. And as I take gamma to 1, I'm really solving an infinite horizon planning problem, which is very difficult. Right, and the catch here is that we understand in a number of different contexts that it's just fundamentally difficult to optimize objectives with large discount factors because it requires planning far into the future. It leads to all sorts of algorithm instabilities, and the punchline is it requires collecting a lot of data to get the system to do what you want when you solve problems of this form. But again, if we come back to the inverted pendulum here, the challenge is that a lot of our robotics objectives are fundamentally long horizon. We need to coordinate behaviors for these systems far into the future to get them to do what we want. And if we think about the normal way we write down objectives for a system like this, the way I would do this is by, let's say, just penalizing the distance from my current state to the upright position, right? This is how we like to use reinforcement learning, by giving the robot points for figuring out that I want to end up at the goal state. But the challenge here is that when we use objectives of this form, this fundamentally requires long horizon planning. And the reason for this is that if I want to get to this goal state where my cost is small, I need to figure out that I have to increase and decrease and increase and decrease my cost over time to eventually get the system to go where I want. And this requires planning far into the future and is just fundamentally difficult. So just to reiterate where we are, The usual way we write down solving reinforcement learning problems in robotics requires solving problems with large discount factors. This means we need a lot of data to get a good solution to the problem we're trying to solve. If we actually want to go solve this in the real world, that's going to require collecting a lot of data, and in many cases, that's just not going to be practical. And at a technical level, in the case of stabilizing controllers, people have shown that if you're actually going to stabilize the system, you often need a nearly optimal policy to guarantee that you're going to do so, right? And so when we put all these together, really the punchline, and we're using stability to be formal and precise here, but the punchline is that we really can't get these systems to do what we want by collecting real-world data and training on that data. So what we're going to try to do is we're going to try to take a play from the control handbook by introducing some magic functions, which in a more myopic fashion somehow capture what we want the system to do. In particular, we're going to try to synthesize this magic function W, which we can decrease myopically at every time step to guide the system to where we want. Okay, so these magic functions are going to be called control-Lyapunov functions, and people often abbreviate this CLF, and I'm going to do that throughout the talk. So control-Lyapunov function, CLF. And if you're not familiar with these, control-Lyapunov functions are really designed around our goal state and built up around the point where we want the system to go. In particular, we're going to design W so that's positive definite, which means it's going to be 0 at the origin, which is our goal state, and it's going to be positive everywhere else. So it has a global minimum at the point we want to go to. This is a slightly more technical condition, but we need it to be radially unbounded, which just means it gets bigger and bigger the further we get away from the goal. So pictorially, this will look something like this, where the level sets of the function are growing the further and further we get away from the origin. And the condition we want is right here, right? So we want there to exist a policy which will decrease the value of W at every time step. Now, this is really powerful because if we can find such a policy, then we can actually be guaranteed that the policy will stabilize the system. Now, just to really drive the intuition home here, you want to think of W as some sort of energy-like function for your system. So this energy bowl, which has a minimum at the point where we want the system to go. And this condition here says that we can decrease the energy of W at every single time step. Now, these functions are amazingly powerful if you can find them because they somehow capture the global structure of stabilizing controllers for your system. In the sense that when I solved the reinforcement learning problem, I had to plan really far into the future, but if I can find a W which satisfies the required conditions, all I need to do is find a policy which satisfies the simple one-step criterion. So somehow this function is baking in the structure of globalizing controllers for globally stabilizing controllers for my system. But there's a catch, and this is the catch that we always run into when using model-based methods like this. So first off, how do I get W? So later on, we're going to see some cases where we can systematically design W for many important classes of systems, but this is really the challenge with a lot of model-based control techniques. Writing down W is just as hard, if not harder, than actually get a stabilizing controller for the system. So, how do I actually get this? We'll touch on this. Whoops. We'll touch on this a little bit later, but let's just keep that in mind. But for the time being, what we're really going to focus on is what if we don't know the dynamics? So I defined this condition using F. I said the whole point of this talk is I don't know F, so what are we going to do? Well, in practice, we actually design W, and this goes for generally how we design model-based control approaches. We design them using some approximate model, which I'm going to denote with F, and they tend to work up to some amount of model uncertainty, but at some point they start to break down, and at that point it becomes unclear how to use these control approaches and the models they're built upon. So if we put these techniques up next to each other, they really have a lot of complementary strengths and weaknesses. So control-Lyapunov functions somehow bake in long horizon information, in this case, information about stabilizing controllers, into a much simpler criterion. On the other hand, we need an accurate model to use these approaches. Reinforcement learning, at least in principle, you don't need any model, but they're very slow to learn long horizon behavior.
I have a quick clarifying question.
Yeah.
So I guess if you're using an approximate model, then your residual also has to satisfy this condition, right? Because if you're going to come to that?
That's the entire point of that problem,
okay.
too.
All right.
Yeah, way ahead of me. Yeah, so what we're going to try to do is handle exactly what Sid is bringing up here, is we're going to try to understand how reinforcement learning and control can sort of come together and overcome these issues. And the way we're going to do this is by formulating a reinforcement learning problem that we're going to go collect with real-world data. And what we're going to do is we're going to add this reshaping term here involving W, which is going to be designed using our approximate model into our original objective. So if we stop and think about what's going on here, what I'm doing is I'm incentivizing controllers which are going to decrease W at every time step. Now, if I decrease W at every time step, I would be stabilizing my model. So what this is saying is this reshaping technique is somehow regularizing or biasing the search for a controller towards solutions which would stabilize my model. So really what this is a technique for sneaking in information about my model into the objective that we're formulating. And what we're going to try to do is understand what happens when I'm solving this reinforcement learning objective. In particular, we're going to look at what happens when we use different discount factors and try to understand what reinforcement learning is doing in these settings. So just to give you an overview of the results we show in this paper, so we show that if we use objectives of this form, we can stabilize the system with smaller discount factors, which means we can optimize our objectives more greedily. We also show that you can get away with a highly suboptimal controller. This in some sense means that we're robustifying the search for a stabilizing controller in cases where you get a highly suboptimal solution, which is going to be the case when you're working with a limited data set. And the technical and the sort of punchline here is that, again, we can get away with stabilizing the system with less data. And the sort of technical caveat we need is that W is in some sense an approximate CLF for the real world. And I'll give you some indication of what I mean by that in just a little bit. But just in the interest of time, we're going to sort of give you some indication for this first point here. But I'm happy to answer questions about the second point. OK, so before we go and analyze our method, I'm actually going to walk you through the sort of standard techniques you use when you're analyzing the stability of the original objective. So the way we try to understand the stability of optimal policies is by really analyzing the optimal value function, which is just the smallest possible cost we can get from every initial condition. And the central object we're going to use is the temporal difference equation. Now, if you've worked with reinforcement learning, you're very familiar with this equation. Oftentimes, our reinforcement learning algorithms explicitly use this equation to try to estimate the optimal value function. And what this thing really does is it captures how the optimal value changes along trajectories generated by the optimal policy, which I'm going to denote with pi star here. And the trick we're going to do is we're going to rewrite this equation so that we have how much v star is changing over one time step on the left-hand side here. We're going to assume that our running cost is positive definite, which is just a sort of standard technical assumption you make in the theoretical literature. And what this means is that v star is also going to be positive definite. So if we can actually show that v star is decreasing along the trajectories, we'll have actually shown that it's a control-Lyapunov function for the real-world system, and that pi is a stabilizing controller. So what we want to show is that the right-hand side here is going to be negative definite. And this first term is great. We assume the running cost is positive, so this is definitely going to be negative definite. But the challenge here is that v star is also going to be positive definite, and in general, it's going to be much larger than the running cost. So if we sort of squint our eyes here, what this means is we're going to need our discount factor to be very large if we want the term in green to dominate and for us to have obtained a stabilizing controller. And so really the punchline here is that when we go solve reinforcement learning problems of this form, really what we're asking is that we somehow are going to learn a control-Lyapunov function from scratch using data. And the catch here is that you need a very large discount factor, and it's very slow to do so. OK, so now we're going to walk through similar steps for the approach we're proposing, and we're going to try to understand how things are different. So let me remind you, with the proposed approach, we started off by designing a control-Lyapunov function using our approximate model. And if we look at the level sets here, which I'm projecting down, the challenge here is that we might be in a situation where we can't decrease the value of W at every single time step at different points in the state space. So for example, at these points here. What we're going to show is that when we solve the reshaped objective, what reinforcement learning is implicitly learning to do is to provide a data-driven correction to the control-Lyapunov function that was supplied by the model. So this is exactly what Sid was getting at. Now, I'll tell you what v tilde star is in just a second, but you'll note that this correction is being scaled by gamma, so intuitively, the bigger the discount factor, sort of the more we're letting reinforcement learning plan far into the future, the bigger a correction is being provided. And the hope here is that when we add this correction to the original model-based term, we'll have somehow learned a control the off on off function for the real world. So v tilde star is actually just the value function for the new reshaped problem we're solving, and we're going to follow exactly the same steps we did on the previous slide. So we write down the temporal difference equation for the new problem. It's a bit hairier in this case. Now we're going to define w tilde star to be the new corrected value function that we learned using data and added to our original model-based term. We're going to plug that in and rearrange this equation, and if you do this, you end up with something very similar, where now what we want to show is that w tilde star is changing over every time step, and if this is the case, we'll have again been in a situation where we obtained a CLF for the real-world system. Now, if you look at this term, it's negative definite again, which is great. But right off the bat, it's not immediately clear what the heck is going on with this term. And the reason for that is if we look at our reshaped objective, we have the opportunity to decrease w at every single time step. So v tilde star can actually be negative. And if it's negative, then this condition is definitely satisfied. OK, so if we put the stability conditions for the two problems up next to each other, they're very similar. So in the first case, we'll have a stabilizing optimal policy if this condition holds. And in the second case, we'll have a stabilizing optimal policy if this condition holds. So really what we want to show is that the new value function is smaller than the old value function, because that means we can stabilize the system using smaller discount factors. And that's really what we show. So really the core result of this paper is to show that if we have an approximate control the off on off function for the real world system, and again, we'll talk about what that means in a second, we can end up stabilizing the system with smaller discount factors because the new value function will be smaller than the old value function. And again, the punchline here is that when this is the case, we can stabilize the system with smaller discount factors. OK, so before giving you a little bit of a hint by what I mean about approximate control the off on off function, let's look at the very special case where we're actually able to design a CLF for the real world. So in the case where we can actually decrease w at every point for the real world system. So to understand what's going on here, let's look at the very special case where we're using a discount factor of 0 and we're planning very myopically over one time step. So in this case, the optimal policy is going to be found by just solving this minimization on the right-hand side here. And we can just ignore the term involving L because it doesn't depend on our policy. So in this case, really what we're doing is we're trying to greedily decrease w at every time step. So really what we're doing here is we're trusting our model to exactly capture the structure of stabilizing controllers for my system. In particular, it's pretty easy to show that in this case, if w is actually a true CLF for the real world system, then the optimal policy will be stabilizing if we use 0 discount factor or in fact using any discount factor that you want. So again, the point here is that if we're in a case where we really feel like we can trust our model, we can obtain a stabilizing controller very efficiently. OK, so the actual technical definition that we use for approximate CLF is pretty hairy, so I don't really want to go into too much detail on that, but I'll sort of give you a picture of what I mean. So we started off by looking at the case where we're solving the original reinforcement learning objective using a very large discount factor. This was very slow, it's very data inefficient, it's not something we can go do in the real world. We just looked at a case where if we have a really good model and we're actually able to synthesize a true CLF for the real world, then we can solve a problem that can be solved very efficiently online. But there's really this middle ground we characterize in this paper where if you don't quite have a true control the off and off function for the real world because your model doesn't quite capture everything about the real world system, well then what we show is that, so in these cases, you might be in a situation where you can't decrease w at every time step. But if you can, so for example, at this point here, but if you can decrease w over several time steps, then you can use an intermediate value of the discount factor. You can effectively plan a few steps into the future, and you can get away with using not a gigantic discount factor and really improving the sample efficiency of obtaining a stabilizing controller. OK, so we just went through a bunch of math. Does this actually work when we go put this on real robots? Let's make sure that this all wasn't for naught. OK, so I'm first going to start off by showing you the example we did with the quadruped at the beginning. So what we did here is we designed a control the off on off function using a reduced order model for the system. And what we did is we designed our policy to try to track a wide range of different velocities. OK, so here I'm showing you how we can sort of expand the idea that I showed you, where in the theory we were just trying to get the system to go to a particular point. And so again, what we do is we first design the CLF using our approximate model, we embed it into our reward function, and then we went and trained with real world data. Now, before I get you the actual hardware experiment, here's just a simple comparison we did between the approach I proposed and sort of the standard cost shaping approach that I did. We've shown very sort of consistently that actually taking this approach and really sneaking in information about your model enables us to obtain good controllers with about an order of magnitude less data. And also our algorithms just had way less variance when doing so. And so we're using the sort of standard model-free soft actor critic algorithm for all of the demos I'm about to show. So again, here's the controller we're able to get after just 3 minutes of data. So here we used a discount factor of 0.4. And here what we were really overcoming is the system really vibrates a lot when it's hitting the ground. And so there's a lot of actually uncertainty between our model and the real world. And really what we did here is we fine-tuned an initial solution that we got from simulation, and we were able to obtain much more accurate tracking performance, even with this small amount of data. So for the second example, I want to come back to this question of how the heck do we get W? So in the previous case, we actually followed a procedure for writing down a CLF that was found in the literature. But for this complex swing-up motion here, it's actually hard to write down a control-Lyapunov function which will somehow capture this complex behavior. And so what we did is we tried to learn a control-Lyapunov function in simulation. So a few slides ago, we saw that if we solve the original problem with a very large discount factor, then the value function associated to that problem will be a control-Lyapunov function for our simulator. So what we did is we solved the original objective using a large discount factor in our simulator. So that took like 1.3 million samples or something like that. We said, OK, we trust this to be a control-Lyapunov function for our simulator. So we took that to be W. Then we followed the same steps we did before. We embedded W into our reinforcement learning objective. And then we went and solved this problem using real-world data. So really what we're doing here is we're using our model to encode this complex behavior into this potential function. So here's the behavior of the initial controller when we deployed it straight from simulation to reality. And it does a pretty good job, but it doesn't quite do what we want it to. And here's the controller we were able to learn after collecting just one real-world trajectory. So it was able to successfully perform the swing-up task. And here, Fernando is going to go poke it. And we actually found that it was pretty robust and able to recover from a lot of different perturbations.
I had a question about Pearson.
Yeah.
How do you know, so when you train it in simulation and get a sort of your approximate policy and run it on the real robot, like zero shot,
Yeah.
And you observe its behavior, like how do you know that it's good enough that this technique would work? Like, is there a signal, or like, because like you've lost some of the guarantees, right? Because you don't know how approximate the simulation is compared to reality.
Yeah, that's a good question. So in this paper that we wrote for Coral, we were kind of after the qualitative story of how do we shorten the effective horizon we're planning over. And to some extent, we're working on a like TAC paper right now where we say, okay, if you have some Lipschitz bound on your dynamics, you can back all that out. But I mean, we don't know what the real world dynamics are. And so I think really what we're after here is just sort of, again, the qualitative story of how do we actually do this efficiently out in the real world.
Yeah, I was going to ask about Lipschitz also because we've done some work on, and we can come back to that later because there are other ways to encode some structure in the dynamics, like assuming it's Lipschitz. And I'm wondering how it's complementary to like assuming something about the value function.
Yeah, that's a great question. So I think we kind of intentionally did this to be complementary to like all of those techniques because this is very intentionally like algorithm agnostic as much as possible.
So they can both work together.
Exactly.
I see.
Yeah.
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 Does that still take less sample when you have to learn the Lyapunov and then transition to real world compared to just learn it from scratch?
It takes less real world data. That's what I care about. Yeah.
So how does this compare to just like fine tuning using RL?
Great question. I'm going to talk about this more in a couple of slides, but this is using analysis techniques from control to set up more efficient and reliable fine tuning setups.
Technical questions like, will deploy the policy directly deploy Pi or still running CLF still in real? you can directly deploy pi, right, as a function state, or you can still run a CLF state or like WX. You just argmin W, right, like x t plus 1 minus WX.
Yep.
Which we are doing.
So for the quadruped, we were using the sort of optimization-based CLF controller. Here we were using a policy that was trained using
Direct is the pi trained from the hybrid approach.
Yeah, right. But like the general approach is kind of agnostic to however you get the initial controller. And what we actually did here is we added like a delta neural net to the initial policy.
And do you need to assume like the standard assumptions have like a control I-found dynamics and unbounded contraction, or this framework is?
So not the way I did it, because here I assumed that there exists a control which decreases it over one step. What you're saying is a fantastic question, and in practice, the way we actually get the ones we design by hand is designing it using a continuous time model, discretizing, and sort of dealing with all those things you're hinting at.
Yeah, thanks.
Cool. Yeah, great questions. Okay, so I'll just very briefly mention, again, we showed you how to do this for a control the op-on-off function, but there's really a very general principle here, where we can use design techniques from control and embed them into the reinforcement learning objectives we're formulating. So in this example here, we want this biped to walk forwards, but we also don't want it to fall into the ground here. And so what we can do is we can formulate a safety constraint, which says, don't put my foot behind this red line, or excuse me, under this red line. And then what we can do is use a technique called control barrier functions, which somehow encode this safety specification in a very similar way to which we encoded stability with the control the op-on-off function. So in particular, I'm not going to go into the detail on these methods, but if you're familiar with them, if this is your barrier function, we can encode safety information into our objective in exactly an analogous way to what we did before. And when we do so, we can obtain this controller which performs precise foot placement after just 3 minutes of simulated data. OK, so I briefly just want to say that I think we're really sort of scratching the surface here in how we can push this principle. So things we're really thinking about a lot now are how can we really scale up this idea if we're in situations where we have things like sparse rewards, like we run into with manipulation? What if we want to be learning at multiple layers of abstraction with hierarchical reinforcement learning? What if we want to do offline reinforcement learning with massive data sets? People understand really deeply at this point that solving problems with small discount factors enables you to do that efficiently and reliably. And can we also integrate these ideas with emerging techniques from domain randomization and adaptation? OK, so we're going to go to part 2 of the talk. And again, really what we're going to do here is, in part 1, we tried to build up an algorithm-agnostic perspective for how we can write down effective reinforcement learning problems. And in this part, we're really going to dig into the algorithms we're writing down and the control architectures we're optimizing over to really squeeze the most out of our approximate physics-based models. So just a little bit of setup. Again, we're going to try to control these unknown real-world dynamics. But now I'm going to explicitly introduce this parameter for our policy. So theta is just going to be the weights of your neural net. We're again going to try to optimize rewards over some time horizon. But now instead of using the discount factor to implicitly control long horizon effects, we're going to introduce this explicit horizon t here and try to understand algorithmic dependencies on this quantity. So we're going to look at policy gradient algorithms, which sort of iteratively attempt to approximate the steps of gradient descent. And I say approximate because we don't know the real-world dynamics. If we did, we could just do all this in simulation. So we need to go collect real-world data to try to approximate the policy gradient. And in particular, what we're going to try to understand is how can we use our approximate physics-based models to really build up efficient and precise policy gradient algorithms, which can learn with small amounts of real-world data. So in particular, a lot of model-based reinforcement learning approaches try to learn a model from scratch fitting something like a neural net nowadays. And what we're going to try to do is try to understand how we can just use some approximate, very coarse physics-based model to really perform these approximate gradient computations. So coming back to this picture here, again, the central challenge with all of this is that our robotic systems are unstable, which means they're highly sensitive. And what this means is for policy gradient algorithms, these approaches have a very high variance. This occurs because the trajectories of my system tend to diverge very quickly over time, which means I need to sort of sample the space very densely if I'm going to obtain an accurate policy gradient estimate. It also means that the underlying optimization problem that I'm writing down is often ill-conditioned. If you're not familiar with what this term means from the optimization literature, it just means that we have to update the parameters of our policy very slowly to maintain an algorithmic stability. So these two problems hold for both model-based and model-free approaches. But for model-based approaches, we have an additional challenge, which is we have a high model bias when we're using model-based estimators. And the reason for this is that small inaccuracies in our model tend to propagate and explode very quickly over time due to the unstable dynamics. And again, the punchline here is that when we're using these approaches, we either have to collect a lot of data to really reliably get the system to do what we want. And again, what this part of the talk is about is really trying to understand systematically how the control architectures we're building up can be used to combat these challenges. So in a lot of real-world cases, we're not just going to directly have a neural net put out an input to our system. We're actually going to pass it through some sort of hierarchical control architecture. And to illustrate what I mean by that, let me show you an example for this RC car, which we're going to try to control in a few slides. So the control architecture we're going to use operates by having some high-level planner spit out some desired trajectory for your system by choosing the parameters of a spline that you want the system to follow. And then there's a low-level tracking controller whose job it is to try to track that desired trajectory. So this controller takes in the current state, it takes in some different feedback gains, and its job is at every point in the state space to see if this is my actual trajectory for the system, in some sense measure the distance between where I am and where I want to go, and to try to push the system back to where I want to be. Now, oftentimes we think of the role of feedback controllers to be to try to somehow very precisely track my desired planned behavior. But we're actually not going to use that feature of feedback controllers here. In fact, to get benefits out of low-level feedback in the context of learning, we don't need our models to be perfect. Really what we need is for the feedback controller to, in some sense, reduce the sensitivity of the system with respect to the inputs that we're putting into it. And so this is actually sort of the key contribution of this work. So if we go back to the sort of naive perspective where I'm just having a neural net spit out inputs into my system, the problem you're going to write down in this case is going to be very sensitive to the parameters of your neural net. But if we optimize through a low-level feedback controller in this hierarchical approach, in the sense that we have our neural net spit out the parameters of our desired spline and the feedback gains, what we show is that this actually reduces the sensitivity of the system response to changes in our neural network parameters. Now what this does is this reduces the variance of policy gradient methods, it solves the issues with ill conditioning, and then what we're going to do is we're going to carefully design a model-based policy gradient estimator where we're really going to build up this estimator around our approximate physics-based model, as I was saying. And when we put all these pieces together, we're also going to overcome the issues with model bias, and we're going to be able to learn very efficiently in the real world in a reliable fashion. So again, we're going to put all these pieces together in a very particular way to be able to learn reliably and efficiently in the real world. And slightly more technically, what we really show here is that in general, if you don't put all these pieces together in just the precise way, you're going to have very bad exponential dependencies on your time horizon for all of these quantities. And this is what really makes it difficult to apply a lot of model-based reinforcement learning approaches in practice. But when we put all these techniques together and really think carefully about how we're designing our policy gradient estimators and the architectures we're optimizing over, we can really overcome these challenges. Okay, so I'm going to give you just a little bit of an intuition for why this is, and to do so, we're going to sort of unroll the structure of the policy gradient. So just as a simplifying assumption, let's forget that we're optimizing over distribution of initial conditions and assume we're just looking at one initial condition. So the policy gradient is going to look like this, where the xt's are the trajectory generated by my current policy from the initial condition. So the policy gradient is given by differentiating L along the trajectory and multiplying it by the sensitivity of the system of the state trajectory with respect to changes in my control parameters. So now let's think, if I knew the real world dynamics, how would I go about calculating this expression here? Well, so essentially what I'm assuming here is that I have a perfect simulator. So what I would do is I would simulate the policy forward in time. I would write down the cost that I get along this trajectory and differentiate them to calculate this first term here. And then you can actually calculate the sensitivity term here by differentiating or linearizing your dynamics along the desired real world trajectory. And again, really the challenge here, and the reason why all of this goes wrong if you're not careful, is that this term tends to blow up exponentially over long time horizons. This leads to your issues with high variance, ill conditioning, and it's very difficult for model-based approaches to approximate. So now let's think how we might do this if we have an approximate model, which I'm again going to denote with f hat here. So the naive way you could do this is by simulating or hallucinating a trajectory for your system forward in time, and you sort of introduce two sources of error when you do this. So the first source of error comes from the fact that I'm predicting inaccurate real-world trajectories, and the second source of error comes from the fact that if I now backpropagate using my approximate model, my derivatives are wrong. And these two sources of error tend to compound in very nasty ways. So the way we're actually going to construct this estimator is by mixing in a little bit of real-world data. So in particular, we're actually going to go collect the real-world trajectory using our current policy. So we're actually going to apply our policy to the real-world system and see what happens. This is going to get rid of the first source of error because we can actually evaluate our loss along the real-world trajectory. Then what we're going to do is we're going to differentiate our approximate model along this trajectory to approximate the sensitivity term. And so really the only approximation we're making here is we're approximating the real-world sensitivity with an approximator which is built using our model. And it's worth sort of meditating on what we're really doing here. Really what we're doing is we're sort of differentiating through our model along real-world trajectories and trusting it to generalize the system behavior to data points that aren't in our data set. But the challenge here is that because this term blows up exponentially, small errors in our derivatives are going to tend to blow up over time, and this one makes it really difficult to actually just do this in practice. But again, what we're doing is we're doing this by integrating feedback into the policy architectures we're optimizing over, and we show that if you do this in just the right way, you can actually overcome these exponential dependencies and everything works out. And to introduce the final technical term for the talk, this is a term from the control literature, which is we need our low-level tracking controller to be incrementally stabilizing. And if you're not familiar with this term, it just means everything that I've been saying. Really, we don't need our controllers to be extremely precise coming from our model. We just need them to somehow simplify the response of our real-world system with respect to our policy parameters. And we have a lot of different control approaches which can satisfy this property. OK, so here is the car example. And this is the tracking behavior we were able to get after collecting just 3 minutes of real-world data. So in orange here is the controller that came from our model-based approach. And we're able to get much more precise behavior after just collecting this small amount of data. So for our next example, we're going to go back to the quadruped we were looking at before. We're still going to try to track this figure 8 behavior. We're going to, again, use a very simplified reduced order model as our physics-based model for the quadruped. Here we actually have multiple layers of feedback that we build up to try to track desired trajectories. And before I show you the hardware example, I again want to show you one more comparison. So here I'm comparing to two standard model-free approaches on the top and a standard model-based approach in orange here, when our approach is in blue. And I want to point out this is not at all a fair comparison, because all these other approaches are really trying to learn, in some sense, the input-output dynamics from the system from scratch. And really what we've shown here is that by wrapping feedback around our model in just the right way, we can learn very efficiently by really trusting our model to capture the basic structure of the real-world system. So I'll sort of let this play. So this is our train controller, which again had much tighter performance than the original solution. And the thing I'll note here is we're using vanilla policy gradients to go learn in the real world. We're not mixing in all of the standard techniques we do in reinforcement learning, like off-policy learning and all of the different forms of data reuse. But by really just carefully integrating feedback in just the right way, even the sort of simplest reinforcement learning methods are now something that we can use efficiently and reliably in the real world.
So if you're thinking about having approximate feedback and you're making the point that that can be very helpful, my intuition is that if the feedback doesn't send you in the wrong direction, then it's going to be fine.
Exactly.
Is that an intuition that is right and that you use?
Yeah, exactly. So this is something we are trying to quantify a bit more, but intuitively you can think of if the model sort of gets the sign right, it's going to be very useful. Yeah. Right, but then the issue is that errors are going to get really bad over long time horizons, but feedback makes everything better. Yeah. Okay, so I'm running a little bit short on time, so I'm just going to click through this a little bit to sort of give you some intuition for where all of this is going. So at a very high level, I sort of opened up this talk by saying, we really want to build up these sort of scalable engineering pipelines which are going to enable us to push these systems out into the real world in a reliable and efficient way. And today we really focused on the control layer and how we can integrate techniques from reinforcement learning and model-based control in a really systematic way to improve the efficiency and reliability of these approaches. But if we're actually going to get our robots out in the real world, there's still a number of challenges we're going to need to overcome. And in the future, I'm really interested in using everything I talked about here today as a foundation for bringing in techniques from perception, human-robot interaction, and at the end of the day, providing a systematic theoretical approaches which don't sacrifice on scalability to deploy these systems out in the real world. So to motivate the need for perception, let's look at a couple of examples. So if we think about this quadruped or this manipulation system here, the dynamics of these systems with respect to their objectives are fundamentally defined by the interactions of these systems with their surroundings. So for this quadruped to make its way through the world, it needs to systematically make and break contact with its surroundings. Now, earlier in my PhD, I spent a lot of time working on model-based methods for planning through contact, and these approaches work really well in simulation, but when we actually go out into the real world, it's often really hard to actually know where the ground is and what sort of the features or the dynamics of your interaction with the ground are. And so if we're going to really sort of continue this program I've been pitching here of using approximate physics-based models to adapt very efficiently in the real world, we're going to have to figure out how we can integrate perception. Now that might be LiDAR, that might be computer vision, but we really need to build up approximate world models around our physics-based models if we're going to adapt rapidly in the real world. And one thing we're thinking about a lot right now is how we can sort of use computer vision to estimate the contact forces that a robot is experiencing as it's making and breaking contact with its surroundings to really build up these sorts of models. So one other thing we really sort of took for granted throughout this talk is that there was a human who was able to specify in a very simple way what your objective is. So here we looked at things like go to a desired point or track some desired trajectory. But in reality, right, we really want to get these systems to perform much more complicated objectives. Right, so I might want my robot to walk across the room, pick up a cup of coffee, and bring it over to me. And we've made a lot of progress in the last decade or so in somehow specifying these sorts of semantic intents to these complex systems, but we've still really had this bottleneck where even if I can specify to the system what I want it to do, actually getting it to do it reliably out in the real world is still a challenge. And so in the future, I think that everything I sort of presented to you here today will provide a really nice sort of algorithmic foundation for continuing to build up these stacks for more and more complex systems and really provide a nice interface from going from the semantic land to sort of driving these intents all the way down to the inputs we're putting into our system. So as just a little bit of a pitch for some other work I did during my dissertation, I've also done a lot of work providing statistical guarantees for nonlinear control. And so a real challenge with all of the problems that I wrote down today is that all of the reinforcement learning problems we solve using realistic robotic systems are just horribly non-convex. We're optimizing over nonlinear dynamics, which introduces non-convexities. We have neural nets. And so it's really difficult to understand what these algorithms are converging to and to provide guarantees for these approaches. And again, I'm just going to sort of give you a teaser for some other work that I've done, but I've really worked on providing statistical correctness guarantees for many different of these optimization-based approaches, and really provided some of the first convergence guarantees for these non-convex problems. So again, the sort of end goal here is to really bring all these techniques together in a really systematic way so that we can, in a scalable and systematic fashion, deploy these systems out in the real world. And things we're thinking about right now are how we can use all of this as a foundation for bringing in guarantees with things like computer vision, and also how we can provide guarantees when these systems are interacting out in the human space. So with that, thank you for coming to my seminar, and I'm happy to take any more questions.
Thank you so much. We have time for maybe one or two questions. No question. Yeah. One of the challenges that we face when you're talking about it, about forces and contacts, is that the dynamics are often non-smooth. You have contact, you make and break contact, and you've seen that in your work. And yeah, so how do you envision dealing with that or approximating that? Of course, there are simulators that sort of soften that and find other ways, like barrier methods and other things that try to find other ways of doing it. But Is there a systematic way to think about it?
Yeah, so what we're thinking about now is, again, sort of what we did in the second part, which is think about the policy representation we're learning over. So we have a lot of very compliant ways to have our robots interact with their surroundings, and yeah, what we're working on now is showing that that's really the right representation if we're going to actually learn with real-world data. Yeah.
But I'm particularly interested in the future direction around the perception, where that comes in. Most of my experience is like, okay, that's the core uncertainty that's better. There's way more uncertainty there than in our system models, let's say. So do you expect the foundational principles to remain the same? Is it that the RL will be accommodating that uncertainty in a way that you can just teach it through the data, or do is there something fundamentally different from what is going on with the interaction of the RL and the control theory?
So I don't think there's anything that's fundamentally different than what's going on with the RL and control theory, but there's more challenges. So if we think about building up some sort of, let's say, perception map around my humanoid robot, the way errors in that model are going to propagate through the system are way harder than if I just have a manipulator arm. So if I'm wrong about where the ground is or the angle of the ground, that's going to propagate through my nonlinear dynamics in horrible ways. So I think that it's upping the level of the challenge of the problems, but I think that if we're smart with how we're sort of wrapping feedback around this entire process, I think it's very doable.
Just as a follow-on, is there an opportunity about specifying the intent more so with the perception? Like, I mean, if I'm thinking that reinforcement learning could come into play with interacting at a higher level of the goal setting.
Yeah. I think there's a lot of opportunities here, and I think that this entire talk, I think, is about really sort of trying to factor out as much complexity at the lower level control process as we can to sort of provide clean interfaces for bringing in perception and this sort of higher level reinforcement learning you're talking about in a sort of, essentially in a cleaner way.
Thank you so much.